Hi friends, this is Naresh. This is my third lecture on mechanics of solids or strength of materials subject. In this session, I am going to explain about Hooke's law and Poisson's ratio uh, and the relation between three elastic constants, that is Young's modulus, bulk modulus, and shear modulus. Okay, before going to the topic, first of all, you have to know the fundamental about the cross-sectional areas because our subject, mechanics of solids or strength of materials, depends upon mainly stress. So the formula for stress is load by area. So load by cross-sectional area. So the cross-sectional area is very important for our subject point of view. Therefore, uh, now I am going to explain about different cross-sectional areas. The first one is solid circular cross-section. This is a solid shaft having length L and diameter D. Okay, this is the diameter D. So this is the cross-section. Okay, this circular shape is a cross section of this solid shaft. So the cross sectional area of this solid shaft is area of a circle, that is the area in terms of diameter equal to pi by 4 d square. Okay, as well as the area in terms of radius is capital A equal to pi r square. Okay, pi into r square is the area for circle, or pi by 4 d square also same for circle, solid circle. Okay, this circle having outer diameter d. Okay, where capital D is the outer diameter of the solid circle. Okay, now here this is a hollow pipe. Okay, hollow pipe. So for this hollow shaft having a cross section, hollow circle. Okay, so here this section consists of two circles. First one is hollow circle, that is inside circle having diameter small d, and other circle is a larger one, that is outside circle capital D. Okay, capital D is the outer diameter and small d is the inner diameter. Okay, so here the formula for hollow circle in terms of diameter is pi by 4 d square. Okay, first of all you have to consider a outside bigger one circle as a solid area, that is pi by 4 d square. Then after you have to subtract the hollow circle, that is a minus pi by 4 d square. Okay, minus small pi d square by 4, that value is area for small circle. Okay, so you have to subtract area, small circle area from bigger circle. Okay, as well as the area of a hollow circle in terms of radius equal to pi r square minus pi r square. Here capital R is the radius of a outer circle, small r is the radius of a inner circle. Okay, so here these are the cross sectional areas for solid circle and hollow circle. Okay, these two are very important in our subject point of view. Okay, now this is a solid rectangle. Okay, this is a solid rectangular bar. Okay, this bar having a rectangular cross section. This solid rectangular cross section having dimensions base capital B and depth or height capital D. Okay, therefore the area for a solid rectangle capital A equal to base into height, that is B into D is the formula for solid rectangle. If if you are considering a hollow rectangular bar, then the dimensions for this hollow rectangular bar as capital B is the outer base and capital D is the outer height. Okay, outside rectangle height. As well as for inner rectangle, small b is the base and small d is the height. Okay, so the area for hollow rectangle as capital A equal to area of a outside rectangle b into d minus area of a inner rectangle small b into d. Okay, this is the formula for hollow rectangle. Okay, here you can observe here, this one is a solid rectangular bar, this one is hollow rectangular bar. Okay, this is the main difference between this one and this one. Now now this is a triangular bar, solid triangular bar having base capital B and height h. Okay, for this solid triangle, area of a solid triangle a capital A equal to half into base into height. Okay, this is the formula for triangle. Okay, as well as this is a square cross sectional bar. Okay, so square bar having dimensions capital B and B. B is the base, height also B. Okay, for square section having four sides equal. Okay, having four sides equal dimension, so base equal to height, that is B equal to B. So that's why the area of a square equal to capital A equal to B into B, that is B square. Okay, now these are the important cross sectional areas in our subject point of view. Now I am going to explain about Poisson's ratio. Before going to explain about Poisson's ratio, first of all, you have to know the fundamentals about linear or longitudinal strain and lateral strain. Okay, so that's why I am going to explain about linear or longitudinal strain. First you have to know the definition of a strain. Strain, the ratio of change in dimensions to the original dimensions is called strain. Okay, where linear or longitudinal strain, the ratio of change in length to the original length of the body is known as linear strain or longitudinal strain. Okay, here this is the original size of a body. I consider a rectangular body having a uh, diameter or height capital D and length L. These are the original dimensions of the body. Okay, original dimensions of the bar. Okay, when we are applying tensile loads or compressive loads. Okay, here I am applying tensile loads, then the length of the bar increases. Okay, and the diameter of the bar decreases. Okay, so for linear or longitudinal strain, the formula is change in length by original length. Okay, so here this is the original length and this one is change in length. Okay, this is the change in length. So the formula for linear strain equal to change in length, that is delta L by capital L. Original length is L. Okay, this is the formula for linear strain, where the positive sign is for tensile loads. Okay, here you have to consider positive sign for tensile loads because when you are applying tensile loads, the length of the bar will increases. Okay, that's why you have to consider positive sign for tensile loads. Okay, similarly, if you are considering a compressive loads like this, when you are applying compressive loads, then the diameter of the bar increases and the length of the bar decreases. Okay, like this. So this is the delta L is the change in length or compressed length. Delta L is the change in length or compressed length. Okay, now this delta D is the increased diameter or decreased diameter. Okay, in the in this case, when you are applying compressive loads, the length of the bar decreases. So that's why you have to consider negative sign negative sign for compressed loads. Okay, for linear strain, positive sign for tensile loads, negative sign for compressed loads. Because in tensile loads, the length of the bar increases, so you have to consider positive sign. And when you are applying compressed loads, the length of the bar decreases, so here you have to consider negative sign. Okay, this is the very important. Okay, this is the formula for linear or longitudinal strain. Now I am going to explain about lateral strain. Okay, uh, here the lateral strain, here also strain is the same formula. The ratio of change in dimension to the original dimension is called strain, whereas lateral strain, the ratio of change in lateral dimensions to the original lateral dimensions of the body is known as lateral strain. Okay, so here also I consider same diagram. Okay, so L and D are the original dimensions of the bar. When you are applying tensile loads on the bar, the length increases, the length of the bar increases, and the diameter of the bar decreases. Okay, this increased length is called change in length. The decreased in diameter is called change in diameter. Okay, so the formula for lateral strain, here length is the linear dimension. Okay, other than length is called lateral dimension. So here the delta D and capital D is the lateral dimension. So here the change in dimension is called change in diameter. So original dimension is called diameter, original diameter. Okay, so the formula here also, when you are applying compressive loads, the diameter of the bar increases and the length of the bar decreases. The compressed length is called change in length, and increased in diameter is called change in diameter. Okay, now the formula for lateral strain equal to change in lateral dimension by original lateral dimension. Here the lateral dimension is diameter, so delta D by D. Okay, here when you are applying tensile loads on a body, the diameter of the body decreases. Okay, when you are applying tensile loads on the body, then the diameter of the body decreases. So here the diameter of the body decreases. That's why you have to consider negative sign for tensile loads. In lateral strain, in case of lateral strain, you have to consider negative sign for tensile loads. Okay, whereas you are applying compressed loads on your body, the diameter of the body increases. So you have to consider positive sign for compressed loads. Okay, in case of compressive loads, you have to consider positive sign. In case of tensile loads, you have to consider negative sign. Okay, now the formula for lateral strain equal to delta D by D, change in diameter by original diameter. Here for linear strain and lateral strain, there is no units for strain. Okay, now now delta D by D, here D is the lateral dimension for circular bars. If in case of rectangular cross sections, okay, in case of rectangular cross sections, L is the linear dimension, and width and thickness of the bar are called lateral dimensions. Okay, width and the thickness of the bar are called lateral dimensions. So the change in width by original width is called lateral strain, and also similarly change in thickness by original thickness is called lateral strain. Okay, and a change in diameter by original diameter is called lateral strain for circular cross section. Change in width by original width, change in thickness by original thickness, these both are for lateral strain for rectangular or square cross sections. Okay, Poisson's ratio. Here it is very important for mechanical subject, because the deformation of the body mainly depends upon Poisson's ratio. Okay, so the formula for Poisson's ratio equal to, Poisson's ratio is the ratio of lateral strain by linear or longitudinal strain is called Poisson's ratio. So the Poisson's ratio equal to lateral strain by linear or longitudinal strain. That is for circular shafts, delta change in diameter by original diameter is called lateral strain, and delta L by L is called linear or longitudinal strain. Yeah, the Poisson's ratio is denoted by symbol mu. Mu or 1 by m. Okay, this is the symbol for Poisson's ratio, and here Poisson's ratio having numerator in here delta d in mm or meter and d also in mm or meter. So no units for lateral strain as well as no units for linear strain. So here in numerator and denominator no units. So that's why the Poisson's ratio also having no units. Okay, so Poisson's ratio has no units. So the value of Poisson's ratio always lies between 0 to 1. Okay, so always the sign for positive Poisson's ratio is positive. Okay, you have to consider positive sign for Poisson's ratio. Okay, it has no units. Hooke's law. Okay, it is very important for all engineering materials. Okay, within the elastic limit, the stress is directly proportional to the strain. Okay, so within the elastic limit, the stress is directly proportional to strain. This is the law for Hooke's. Okay, so in Hooke's law, the stress is directly proportional to strain, whereas linear stress or shear stress or any type of stress, that stress is directly proportional to corresponding strain. Okay, so yeah, the stress is directly proportional to strain, and this stress is denoted by symbol sigma, and strain is denoted by symbol epsilon. Okay, so this is the formula for Hooke's law. Now coming to the another one, that is types of moduli. Okay, types of modulus. It is also very important for predict the strength of the material. Okay, these three here there are three modulus are in our subject point of view. These three modulus are very important to predict the behavior of the material. Okay, Young's modulus, first one is Young's modulus or modulus of elasticity. Okay, this one is used for determining the elasticity of the body. Okay, this first modulus is useful to predict the elasticity of the materials. Okay, and the second one is shear modulus or modulus of rigidity. Okay, this second one is used for identify the behavior of the body or behavior of the rigidity. Okay, and third one is the bulk modulus. Okay, here here the bulk modulus is used for predict the behavior of the volumetric bodies. Okay, Wa- here the units for Young's modulus, shear modulus or bulk modulus are same as stress. Okay, because the formula for Young's modulus is stress by strain. Okay, shear modulus also stress by strain. Bulk modulus also stress by strain. Okay, so the strain has no units. So the units for three modulus are same as stress. Okay, so the units for stress is Pascal. Okay, 1 Pascal equal to 1 Newton per meter square. This is the unit for SI unit for stress. Okay, this is also unit for pressure. Okay, this unit is the same for pressure. So here the Pascal is equal to 1 Newton per meter square in SI units, and if you are taking in kilopascal, then 1 kilo equal to 1000 Newton per meter square. Similarly, 1 megapascal equal to 1 mega equal to 10 power 6 Newton per meter square. Okay, whereas in terms of mm, 1 megapascal equal to 1 Newton per mm square. Okay, 1 megapascal equal to 1 Newton per mm square. Similarly, 1 gigapascal, where G is the giga, M is the mega, K is the kilo. Okay, so 1 gigapascal equal to giga means 10 power 9, pascal equal to Newton per meter square. Okay, if you want to convert this value in mm, then 1 gigapascal equal to 10 power 3 Newton per mm square, because 10 power 6, 1 mega equal to 10 power 6 Newton per meter square. Okay, so that's why 10 power 3 Newton per mm square equal to 1 gigapascal. Okay. So these are the units for Young's modulus, shear modulus, bulk modulus, or stress. Okay, these all are units for stress as well as the units for modulus. Okay. Now, now I will explain about one by one. Young's modulus are also called modulus of elasticity. Okay, Young's modulus or modulus of elasticity. Within the elastic limit, the linear stress is directly proportional to linear strain. Then the proportionality constant is known as Young's modulus. It is also known as modulus of elasticity. Okay, this property is useful to determine the uh, to determine the value of elastic strength. Okay, now by using this property you can predict the behavior of the material, behavior or strength of the material. Okay, so it is denoted by symbol capital E. Okay, the formula for Young's modulus equal to the stress, linear stress is directly proportional to linear strain. So sigma directly proportional strain, then the constant, the proportionality constant, stress by strain equal to proportionality constant. Then the proportionality constant is called modulus. Okay, Young's modulus. It is denoted by symbol capital E. Okay, Young's modulus is denoted by symbol capital E. Okay, so the formula for Young's modulus or modulus of elasticity equal to capital E equal to sigma by epsilon. Sigma is the stress, linear stress. Epsilon is the linear strain. Okay, so here the linear stress means tensile stress or compressive stress. Here the linear strain means compressive strain or tensile strain. Okay, so here the units already we have discussed in previous slide. The units for Young's modulus is same as stress. Okay, now coming to the another topic, that is shear modulus. Shear modulus or modulus of rigidity. This modulus is useful to determine the strength of the shafts. Okay, that is a rigidity of the shafts. Okay, okay, this is a very useful property for determining the behavior of the shaft materials. Okay, so the definition for shear modulus or modulus of rigidity is within the elastic limit. Within the elastic limit, the shear stress is directly proportional to shear strain. Okay, within the elastic limit, the shear stress is directly proportional to shear strain. Then the proportionality constant is known as shear modulus. Shear modulus also known as modulus of rigidity. Okay, so shear stress is directly proportional to shear strain. Then the symbol for shear stress is tau. Okay, now the symbol for shear strain is pi. Okay, now tau divided by pi equal to proportionality constant. Okay, this proportionality constant is equal to the shear modulus or modulus of rigidity. The shear modulus or modulus of rigidity denoted by the symbol capital C. Okay, capital C. Capital C is the symbol of shear modulus or modulus of rigidity. And there are two another symbols are there, that is capital G or capital N or capital C. These three are the symbols for shear modulus or modulus of rigidity. Okay. Finally, the formula for shear modulus equal to tau by pi. Tau is the shear stress and pi is the shear strain. Okay, and the units are same for stress. Okay. Now coming to the last type of modulus, that is a bulk modulus. Okay. Now this bulk modulus is useful for predict the behavior of the solid bodies. Okay. So the formula or the definition for bulk modulus is the ratio of the ratio of direct stress to the corresponding volumetric strain is called as bulk modulus. Okay, the ratio of direct stress to the volumetric strain is called bulk modulus. So here the direct stress is denoted by symbol sigma, and volumetric strain is denoted by symbol epsilon v. Okay, epsilon suffix v. Okay, yeah, the volumetric strain means uh, the ratio of change in volume to the original volume is called volumetric strain. So epsilon v equal to delta v by v. Okay, so epsilon volumetric strain equal to change in volume by original volume. Okay, so where sigma is the stress. Okay, here the volumetric strain has no units, and so therefore the units for bulk modulus are same as stress. Okay, it is denoted by symbol K. Okay, K is the symbol of bulk modulus. So the formula for bulk modulus K equal to sigma by epsilon V. Okay, no here the units are same as stress. Okay, now I am going to explain about relation between three elastic constants. This is the last topic in today's session. Okay, now first of all, already we have already I have explained in previous slides. Elastic constants means Young's modulus, bulk modulus, shear modulus, and Poisson's ratio. Those four modulus are called elastic constants. Okay, so the Young's modulus or modulus of elasticity, capital E, shear modulus or modulus of rigidity, capital C or G or N, and bulk modulus, capital K. These three are called elastic constants. Okay. Now the relation between Young's modulus, shear modulus, and bulk modulus are capital E. Capital E equal to 2C into 1 plus mu equal to 3k of 1 minus 2 mu equal to 9kc by 3k plus c. Okay, here mu is the symbol of Poisson's ratio. Okay, already we have discussed about this Poisson's ratio in this class. Okay, Poisson's ratio is the ratio of lateral strain by linear strain. Okay, mu equal to Poisson's ratio. It is also denoted by symbol 1 by m. Okay, so the formula for Poisson's ratio equal to lateral strain by linear strain, that is delta d by d by delta l by l is the formula for mu. Okay, so mu or 1 by m is the symbol of Poisson's ratio, where capital E is the Young's modulus or modulus of elasticity, and C is the shear modulus or modulus of rigidity. Okay, and K is the bulk modulus. Okay, so this is the relation between Young's modulus, bulk modulus and shear modulus. Okay. Okay. Okay, friends. In next class, I will explain some problems on simple stresses. Okay, simple stresses and Young's modulus problems. Okay.